We want to talk on this video about what's known as the second derivative, and this is section 2.5 in our book. So if we consider the function f of x equals x to the fifth, we have learned from the power rule then that the derivative of f, which we can write as f prime of x, we bring the exponent out in front, subtract 1 from that exponent, and a new exponent becomes 4, so it's 5x to the fourth. Alternatively, we can use our Leibniz notation and say dy dx is that 5x to the fourth. Now notice that this f prime of x, however we write it, is itself a function of x. So it makes perfect sense then to take the derivative of that function. And the way we denote that in the function notation is to make it an f double prime. So we write the second derivative, and this is known as the second derivative, the derivative of the derivative. And so we write it f double prime, and now we bring that 4 times the 5 is 20. We subtract 1 from that exponent 4, and it becomes x to the third. So f double prime of x equals 20x to the third, or 20x to the third is the second derivative of f of x equals x to the fifth. The notation in Leibniz notation can be a little bit confusing, so we just have to get used to it. We write the second derivative of y by writing it looks like an exponent over the d, and then we say with respect to x twice, so on the bottom the exponent goes over the x. So it's d squared y over dx squared, or the second derivative of y with respect to x twice. And so that too then is known as 20x to the third. Now let's talk about the meaning of these various things. So first let's kind of recap or maybe consider the meaning of f prime of x. So f prime of x, remember, is the instantaneous rate of change of f. It's that rate of change. So what we get from that is when f prime of x is positive, then we know that our function must be rising from left to right. That is, we say that f is increasing. So we can use the first derivative as a way of determining or arguing or maybe proving that the function is increasing. When its derivative is positive, the function is increasing. And similarly, when the derivative is negative, when it's less than 0, then that means that our function f is going to be decreasing. So it will be falling from left to right. Now, we have said that a function, if f is always increasing or always decreasing, so always increasing or always decreasing, one or the other, then we say that it is strictly monotonic. So that we have said means that it is monotonic. And I will say strictly in parentheses. Sometimes we don't say that, but we sometimes need to be careful. If I can just spell it right, we'll be in business. So that's going to be monotonic. Now we can see then that our derivative can be a way of telling that that is strictly monotonic. So from here we can see if f prime of x is always positive for a given function, then that means it's going to be monotonic. Or likewise, if the function is always, the derivative is always negative, then that would mean the same thing, that it's always decreasing. So then we move past f prime, and let's talk about f double prime of x. So with f double prime, remember, it's the derivative of the derivative. So it's the rate of change of f prime of x. So if the second derivative is positive, that means that f prime of x must be increasing. It must be rising, or I'm sorry, not rising from left to right, but it is increasing on that interval. The derivative is increasing on that interval. Let's see what that means. I'm going to give you a picture here. So here is a piece of a function right there. Now, if we look at the rates of change, the slopes of the tangent line to that curve, we can see here we get a fairly big negative. Now we've moved to a flatter or a smaller negative. So if this was, say, a slope of -1, and maybe this had a slope or a derivative of -1/2, and then 0, as we move along this way, we can see that those slopes, those derivatives, are getting bigger. -1/2 is bigger than -1, 0 is bigger than -1/2, and then maybe we have a slope of 1, which is bigger still, and maybe a slope of 2 or 3 or something that's bigger still. So we can see from this picture a couple of really important things. The first is that we can see, in fact, that f prime of x is indeed increasing. The derivatives, or slopes of the tangent lines, are getting bigger as we go from left to right. Now we can also see that the curve, that original function curve, lies above its tangent lines. I'm going to say that. So that's an important feature. So we have this phenomenon, that f prime of x is increasing and that the curve lies above its tangent lines. Both of those refer to this curve that we see. Its shape is kind of a bowl-shaped up, is how we would describe that. Bowl-shaped up is that curve. And what that means then is that that is concave up. We say f is concave up on that interval. So all those things all go together. When a function is concave up, the curve will lie above its tangent lines. F prime will be increasing, which means that f double prime is going to be positive. Notice that this is a separate question from increasing and decreasing. On this white curve, which is concave up over the entire interval that we see it, this curve is sometimes decreasing and then sometimes increasing, but it is concave up for the whole interval. So the question of increasing and decreasing and concavity are different. Okay, and that's important to keep in mind. Similarly then, if f double prime of x is negative, that means that f prime of x must be decreasing. And we can see a picture of that. If I draw a curve that is bowl-shaped down, then if we look at its tangent lines, you can see that as we go from left to right, these tangent lines are going to be decreasing. So here the tangent line might have a slope of, say, 2. Now here maybe a half, here maybe a -1/2, here maybe a -3. So as we look at those from left to right, we can see that the f prime of x is decreasing. We can see that the curve lies below its tangent line. So the curve lies below its tangent lines. We will say the curve is bowl-shaped down. That's how we would describe that, bowl-shaped down. And this then is known as concave down. We say f is concave down over that interval. And again, you can see that it's a different question from increasing, decreasing. This white curve that we see here is concave down over the whole curve, all that we see, but it is increasing for this piece and decreasing for that piece. So concavity and increasing, decreasing are different questions. Now, we may want to try, well, we do want to try to come up with kind of a conclusive determination of how to use the second derivative with concavity, but we have to be a little bit careful. Clearly, when the second derivative is positive, that it is concave up. When the second derivative is negative, it's concave down. The question is, what about if the second derivative happens to be 0? And so that is not going to preclude us from including that in the concave up or concave down interval. So for an example, if we look at f of x equals x to the fourth, we know that the graph of x to the fourth is like a very steep, very narrow parabola type thing. So you can see from looking at it that it's going to be concave up everywhere. Now, its first derivative we know is going to be 4x to the third. Its second derivative is going to be 12x to the second. So we can see that the second derivative is 0 at x equals 0, but yet we will still say that it's going to be concave up over the entire interval. So the takeaway is that we will say, here's our kind of fun fact thing here. If the graph of f is concave up and f double prime, it's supposed to be an f double prime, exists on the interval, exists, I'll say on an interval, then f double prime of x is greater than or equal to there on that entire interval. So concave up, we're gonna include just a point at 0 there, as long as it's only at a point and it's positive on either side. And in a similar fashion, then f double prime of x can be less than or equal to 0 when the original function is concave down. Okay, so let's get a new panel here. So let's try to explore this a little further. So I'm going to give you a graph of a function here. So I'm going to put down an xy axis. I'm going to draw a curve here and do something, like something that looks like a cubic here. So this is our y equals f of x. And I'm going to label some interesting points. I'm going to call that point A. And I'm going to call this point right here point B. And we'll call this point right here point C. So we want to see the difference between how we describe the intervals when f is increasing and decreasing compared to when it is concave up and concave down. So when we talk increasing, decreasing, we include the endpoints as long as the function is defined there. So we would say that this function is increasing all the way on the left up to this point where x equals a, and then also from c all the way to forever. So what we will do there is say that is increasing on the interval from negative infinity, which we can never include, up to, and we will include a in the interval where it's increasing. Likewise, we will include c on the interval where f is increasing, and we'll go all the way out to infinity, which we can't include. In a similar fashion, this will be decreasing when this curve is falling from left to right. And we will include the intervals there as well. So even though it seems kind of weird, A and B get included both in the interval where the function is increasing, but also where it is decreasing. Now it looks a little different for concavity. So we can use this symbol, that little U symbol, for where is f concave up. So where we're seeing as concave up is going to be from this point right here and forever to the right. So B is our boundary point between where it goes concave down and concave up. So we will name that later. We will say that that point B, and it looks like its y coordinate is 0 there. Remember, points we try to label as ordered pairs. So B, comma 0, we are going to call an inflection point, or also sometimes a point of inflection. So B is an inflection point, or can be also called a point of inflection, and it will oftentimes be abbreviated as a POI, for point of inflection. Now back to the concavity issue. While we include the endpoints on increasing, decreasing, if the function is defined there, we will never include endpoints on intervals where the function is concave up or concave down. So it will be concave up on the open interval from b to infinity, and it will be concave down on the open interval from negative infinity to b. So that point b is not part of an interval where it is either concave up or concave down, neither one. Okay, so at that point, we don't really talk about concavity as a point-wise characteristic. It's over an interval. And so we just will talk about the intervals where it is concave up and is concave down, and we won't include the boundary points. So let's look at a different kind of graph here. So I'm going to graph another one, and maybe I'll make this look like a different kind of cubic. So something that looks like this. And what we're going to try to do here is see, can we imagine what the graph of y equals f prime of x is going to be, given that this function we're looking at is our f of x. And this is going to be something that we're going to talk about a lot in the days that come, is can we see a graph of a function and understand what its derivative graph will look like and what its second derivative graph will look like, and we can use any of those as a starting point. So eventually we're going to say, okay, if this was a derivative graph, what would its original graph of the function look like, as well as the graph of the second derivative? But that will come in time there. Those can be very challenging questions. So let's first try to graph in green the derivative. So we're going to look for help. Looks like there's a horizontal tangent at these two places, and so that means there's going to be an x-intercept. That's where the derivative f prime is going to be 0. Now it looks like somewhere in here that maybe the slope of that tangent line is about 1. So I'm going to say maybe the y value is going to be about 1 right there. We can see that all along here, the slopes of the tangent line, the derivative, are, I will say the function is increasing, so the slopes of the tangent lines are going to be positive, so the derivative must lie above the x-axis. You can also see that as we move along looking at slopes of tangent line, that this point right here, which not coincidentally is where it changes from concave up to concave down, what we've called an inflection point, that's going to be where the tangent line is its steepest. The slope of the tangent line where it's steepest is going to be its biggest. So we're going to have positive slopes in here, with the largest one happening where we have that inflection point. Now, when we look over here, the slopes of the tangent line are going to be a little bit negative, bigger negative, and they're going to get steeper and steeper negative. Steeper negatives have slopes that are bigger negatives, so our curve is going to do something like this. And similarly, these tangent lines get steeper and steeper, which means their y-coordinates of the derivative are going to be bigger and bigger negatives. And so we're going to get something like that. And we would expect that, right? From what we know about a derivative, if our original function was a cubic, a third degree, we would expect the derivative is going to go down a degree. It's going to be some kind of x squared. It's going to be a parabola. Now we can look, and from there, let's see if we can also graph y equals f double prime of x. And so now we're going to look at the green graph, and again, look for help. We see a horizontal tangent line there. I'm going to put an x-intercept there. We can see that the tangent lines are all positive to the left, and it looks like they're going from big positives over here to smaller positives, and likewise it's going to go negative over here, small negatives, and then bigger and bigger negatives. We would expect that if the graph of the first derivative was a quadratic, that the next derivative, the second derivative, will go down a degree and is going to be linear. And so we're going to get something that is positive to the left there and negative to the right, and a straight line. We'll be spending more time with that. Let's go to another panel here. And we're going to look at an interesting curve called a logistic growth curve. So we haven't seen much of this, if at all, before. This is something we spend a lot of time on in BC calculus, but it has some interesting features here. So I'm going to draw this curve. So it's going to look something like this, kind of like a stretched out S. And usually we just start it at the y-axis, so it doesn't typically go forever to the left. And I'm going to show it where it's got a horizontal asymptote here, and I'm going to call that asymptote L, that y value L. And I'm going to say, let's look at that place right where it changes concavity, and we'll call that T sub 0. And again, we're going to call this, logistic growth curves are oftentimes population growths. So what happens in real life is that the population may grow exponentially initially and take off like it's going to be exponential, but it's hard for a population to continue to grow exponentially forever because it's just not sustainable. So what happens usually is at some point in time it levels off, and we sometimes call this L the carrying capacity, or it's the largest sustainable population that can live in wherever it is, whatever that area may be. So this is maybe an improvement on a population model that than just an exponential model. So our P of T is going to be our population model. The T is going to stand for years. And let's say then that for, we can see that for T greater than 0, that our population is increasing forever. So that would mean, according to what we said, it's derivative, and we can emphasize what's the dependent variable, population, and the independent variable, time, by calling it dp dt, and we can see that that's greater than 0 for all values of t greater than or equal to 0, so where our population is defined. Now we can also see that it is concave up until we get to t sub 0. So that means we can say for t, what do I want to see? I want to say for t that is greater than or equal to 0 but less than t sub 0, our second derivative, and we write that as d squared p dt squared, that's going to be positive. So the population, the population growth is increasing. So the rate at which it's the population is increasing. And we can see that for t greater than t sub 0, that goes on to infinity, that it changes to concave down. And so we would say the second derivative of p with respect to t twice is going to be negative on that interval. Okay, now suppose this is a population of rabbits. So we're going to say that P of T is a population of rabbits, and it's going to be the number of rabbits and T is going to be in years, we said. So we're talking about the number of rabbits in a year, in a particular year. So we could say then our notation is, and our units, if we look at that second derivative of P with respect to T twice, then this is going to be, we know that dp dt, let me back up a little bit, dp dt is going to be rabbits per year. So those are going to be the units for our first derivative. And the second derivative is going to be the rate of change of the first derivative with respect to t again. So you could correctly call this the rabbits per year, which sounds weird but is correct, or it is true, and this seems maybe even stranger, you can call that rabbits per year squared. And that 2 is correct units for the second derivative. Okay, I'm going to go to a new screen here. So I have put a table up here that shows some data that I just made up. But over here we can see particle motion is a very common problem that comes up in AP Calculus. It gives us a nice way of talking about an application of first and second derivatives. So in our particle motion problems in this class, always we will be moving along a straight line. So you can imagine, horizontally, kind of like a squirrel running along a really tight power line there. We can, start at a position of 0 and we can go to the right or we can go to the left. And if we end up at the right, then our position will be at a positive location. And if we end up left, we will be at a negative location. And when we talk about velocity, our rate of change, then that velocity will be positive when we're moving to the right, and it will be negative when we're moving to the left. Okay, so in general now we say if S of t is our position, then we will say velocity is, we will often call v of t, and it is the first derivative of position. And we can write that either as s prime, or as you know, we could use our Leibniz notation and also refer to it as ds dt. Then acceleration, so acceleration, which we often call a of t to represent acceleration, is the derivative of velocity. So it's the first derivative of velocity, which then makes it the second derivative of position. And we can also write that in Leibniz notation as the second derivative of s with respect to t twice. So that's the notation and symbolism that we will use. Now, when we look at this table here, I have some t values and some position values. Now, you can't assume, unless there's other information given to us, about what happens in between these two time values. Now, if it is position, it can't be too wild and crazy. That is, it probably has to be continuous if we're going to talk about the position. We can't really jump from one place to another without passing through the points in between. But we can't really assume that this is going to move from position 0 to position 3 in any particular way. For all we know, we might have gone left for a while and then come back and gone right. We just don't know without more information. But I want to talk about just kind of some trends to notice here. So if this was behaving nicely and predictably, which we don't know, but if it did, you can see that as the position goes from 0 to 3 to 7, each of these position values is bigger than the one before it. So at least it looks like the velocity would be that the position is increasing, which we would then think that the velocity v of t would be positive for whatever values that we would come up with in this interval. And in a similar way, if we kind of look at this, now if we look at the rate of change of the velocity, so from time 0 to time 2, we increased by 3, and here we increased by 4, so that would suggest that the velocity was increasing, which means the acceleration would be positive, at least so far. And then from here we go position 7 to 12. Now it's increased even more. It's increased by 5. So it appears anyway that at least up until right here that the acceleration is positive. Now we don't really know that exactly, but I'm just talking appearances here. Then we can see that in between here, now it increased by 3. That's less than the increase it was before. That means that our rate of change of position, our velocity, is decreasing. And likewise from here to here, it increased by only 1. that would lead us to believe that possibly, anyway, that acceleration is decreasing in there. Our second derivative would be negative. Trying to make some sense out of all of this first and second derivative stuff. So let's take a look at another one. So we're going to say, I'm going to pause it and get my information down and then bring you back. Okay, so here we have, again, a particle is moving along a straight line, and we're assuming here it's going to move like along the x-axis. So here is our position in yellow here, and so this is going to be time along here, and this is going to be our position of that particle. So where is it on that? We can think of it as being a number line. And so we started at 0 position, and then we went up to here, and then so on. So the first question, A, is when is the particle moving to the right? So that is going to be when its derivative is positive, and when we look at the graph, we can see that its derivative will be positive when the graph is rising from left to right. So there's going to be a couple of those regions in there. And so remember, moving right means, in this case, not including that endpoint. So we would say from 0, for t between 0 and p, but not including p, because right at p, that's where its velocity, the derivative, is going to be equal to 0. And to be moving to the right, the derivative has to be positive. Now, it is also moving to the right, we can say, for t greater than r. Okay? It's moving left when the derivative, s prime of t, is negative. And that's when it's going to have negative slope, when it's going to be falling from left to right. And again, we can't include here in this motion question the endpoints, because at those places the velocity is 0, and so it's not moving to the right. So the answer then to part B, when is the particle at rest, that is going to be when v of t is actually equal to 0. So it's not moving right, nor is it moving left, it's just momentarily pausing. And so that's going to be at that t equals p, and also at t equals r. So when is the acceleration 0? That's going to be, well, we know that it's going to be concave up when its second derivative is positive, and it's going to be concave down when its second derivative is negative, and that's going to tell us information about the acceleration. But where it changes from concave down to concave up is going to be when that acceleration or second derivative is equal to 0. And so that is going to be at t equals q, I guess we call that. So let's also ask, where is the acceleration positive and where is the acceleration negative? So I'm going to make that a question. So again, the acceleration will be positive when the second derivative is positive, and that's going to be when the function is concave up. So visually, we can see that is going to be for t greater than q. And again, we can't include the endpoint on anything to do with concavity. And it'll be, the acceleration will be negative when that second derivative is, what do I want to say? It's going to be positive. I don't think I said that over here. So let me fix this one. So second derivative being positive is concave up. I got to get this right. Positive is concave up, and negative is negative is going to be concave down. And that's going to be for 0 less than t less than q. All right, you can give homework number 20 a try.